The question sounds almost like science fiction at first. Is artificial intelligence quietly consuming the world's water? Yet behind the sleek interfaces, instant answers, and endless automation lies a vast physical infrastructure, one that depends not only on electricity, but also on something far more fundamental: water. Every time a user interacts with an AI system, whether generating text, images, or analyzing data, that request is processed inside massive data centers. These facilities, operated by companies like Google, Microsoft, and OpenAI, house thousands of servers working continuously. And like any high-performance machinery, these servers generate enormous heat. To keep them functioning, cooling systems are required, and that's where water enters the equation. In traditional cooling systems, water is used to absorb and dissipate heat produced by servers. This process, known as evaporative cooling, is highly efficient but also water-intensive. In some cases, a single large data center can consume millions of liters of water per day, especially in regions where ambient temperatures are high. Now consider the explosive growth of AI systems, particularly large language models and generative AI platforms. Training these models requires enormous computational power, often running for weeks or months across thousands of GPUs. The hidden cost of this process is not just energy consumption, but water usage on a scale that most users never imagine. Recent studies have begun to quantify this impact. For example, researchers estimate that training a large AI model can indirectly consume hundreds of thousands of liters of water, depending on the location of the data center and its cooling methods. Even everyday usage adds up. A simple interaction, like asking an AI a few questions, may seem negligible, but when multiplied by millions or billions of users worldwide, the cumulative water footprint becomes significant. This raises a critical question. Are we trading convenience and innovation for environmental strain? The issue becomes even more complex when we consider geography. Many data centers are strategically placed in areas with access to cheap electricity, but not always abundant water. In drought-prone regions, the competition for water resources becomes more intense. Communities, agriculture, and ecosystems already under pressure may find themselves indirectly competing with digital infrastructure. This tension is not hypothetical. It is already being debated in parts of the United States, Europe, and Asia, where local populations are questioning the sustainability of large-scale data center expansion. However, the story is not entirely one-sided. Tech companies are increasingly aware of the environmental impact and are investing in solutions. Some are experimenting with air cooling, seawater cooling, or closed-loop water systems that recycle water instead of consuming it. Others are relocating data centers to colder climates where natural cooling reduces the need for water altogether. Still, these solutions are not yet universal, and the pace of AI adoption may outstrip the implementation of sustainable practices. At its core, this issue reflects a broader truth about modern technology. The digital world is not as intangible as it seems. Every search, every AI-generated sentence, every automated decision has a physical footprint. Water, one of the planet's most precious resources, is now part of the hidden cost of intelligence at scale. As AI continues to evolve and integrate into every aspect of life, understanding and managing this cost will become increasingly important, not just for tech companies, but for society as a whole. And so the question remains open, inviting deeper exploration. Is artificial intelligence merely a tool of progress? Or is it quietly reshaping the balance of our natural resources in ways we are only beginning to understand? To truly understand the scale of water consumption tied to artificial intelligence, it is necessary to step deeper into the life cycle of an AI system. Most people only see the final layer, the interface where questions are answered instantly. But behind that simplicity lies a multi-stage process involving data collection, model training, deployment, and continuous optimization. Each of these stages contributes directly or indirectly to water usage. Among them, the most resource-intensive phase is undoubtedly training. Training a large AI model involves processing enormous data sets through powerful hardware, such as GPS and specialized accelerators. These machines operate at extremely high temperatures when pushed to their limits. To prevent overheating, data centers rely on cooling infrastructure that often uses water as a primary medium. In facilities run by companies like Google and Microsoft, cooling towers evaporate water to remove heat, a method that is efficient but results in water loss. Unlike closed systems, where water is recycled, evaporative cooling releases water into the atmosphere, meaning it must be constantly replenished. But training is only part of the story. Once a model is deployed, it enters the inference phase, the stage where users interact with it daily. This phase may seem less demanding per request, but its cumulative effect is enormous. Millions of queries per second across global platforms translate into continuous server activity, sustained heat generation, and ongoing cooling requirements. In other words, even the simplest AI interaction contributes to a persistent, invisible demand for water. An important factor that influences this impact is location. Data centers in cooler climates, such as Northern Europe, can take advantage of natural air cooling, significantly reducing their reliance on water. In contrast, facilities located in hotter regions require more aggressive cooling strategies, which often means higher water consumption. This creates a paradox. Some regions that invest heavily in digital infrastructure may also be those least equipped to handle additional water stress. Another layer to consider is the concept of water footprint displacement. When a company trains a model in one region but serves users globally, the environmental cost is localized while the benefits are distributed. A user in one country may unknowingly contribute to water consumption in another, where the data center is physically located. This disconnect makes it difficult for individuals to fully grasp their role in the broader environmental impact of AI. There is also a seasonal dimension. Studies have shown that water consumption for data center cooling can increase significantly during hotter months. This means that the environmental cost of AI is not constant. It fluctuates with climate conditions. As global temperatures rise due to climate change, the demand for cooling, and therefore water, may increase even further, creating a feedback loop that intensifies the problem. Despite these challenges, innovation is beginning to reshape the landscape. Companies like Google have explored using reclaimed wastewater for cooling, reducing reliance on potable water supplies. Microsoft has experimented with underwater data centers, submerging servers in ocean environments to leverage natural cooling. Meanwhile, researchers are developing advanced cooling technologies, including liquid immersion systems that use specialized fluids instead of water. Yet, these solutions raise their own questions. Are they scalable enough to meet the growing demand for AI? Do they introduce new environmental trade-offs? And perhaps most importantly, will they be adopted quickly enough to keep pace with the exponential growth of artificial intelligence? At this point, it becomes clear that the relationship between AI and water is not a simple cause and effect scenario. It is a complex system shaped by technology, geography, climate, and human behavior. The more AI becomes integrated into daily life, from business automation to content creation, the more this hidden dependency on water will expand. What makes this issue particularly compelling is its invisibility. Unlike factories or power plants, data centers often operate quietly in the background, out of sight and out of mind. Their impact is not immediately visible, yet it is deeply intertwined with the resources that sustain life itself. As we move forward, the challenge will not be to halt technological progress, but to align it with environmental sustainability. The next phase of this story will explore how governments, researchers, and industries are beginning to respond, and whether those efforts are enough to balance innovation with responsibility. As awareness of artificial intelligence's environmental footprint begins to grow, governments, researchers, and environmental organizations are starting to respond. What was once an overlooked issue, hidden behind layers of digital abstraction, is now becoming part of public debate. Policymakers in regions like the European Union and parts of the United States are asking difficult questions. How much water should data centers be allowed to consume? Should there be limits in drought-prone areas? And how transparent should companies be about their resource usage? One of the biggest challenges in addressing the issue is the lack of standardized reporting. While companies such as Google and Microsoft have begun publishing sustainability reports, the data is often aggregated, making it difficult to isolate the specific water footprint of AI systems. For instance, water usage might be reported at the company level rather than broken down by individual data centers or services. This lack of granularity makes it harder for regulators and the public to fully understand where and how resources are being consumed. At the same time, environmental groups are pushing for greater accountability. Organizations like Greenpeace have long advocated for transparency in energy usage, and now water is becoming part of that conversation. The argument is simple. If artificial intelligence is going to become a foundational layer of modern society, then its environmental costs must be clearly measured and responsibly managed. Without transparency, there can be no meaningful regulation or improvement. In response to growing pressure, some governments are considering new policies. These may include restrictions on building data centers in water-scarce regions, incentives for using recycled or non-potable water, and requirements for companies to disclose detailed environmental metrics. In certain areas, local communities have already begun to resist new data center projects, particularly when they fear competition for limited water resources. This tension highlights a broader issue: the balance between economic growth and environmental sustainability. Meanwhile, the research community is exploring ways to make AI itself more efficient. One promising direction is the development of smaller, more optimized models that require less computational power. Instead of relying solely on ever larger systems, researchers are investigating techniques such as model compression, distillation, and more efficient training algorithms. By reducing the computational load, these approaches can indirectly lower both energy and water consumption. Another important area of innovation is software optimization. Even small improvements in how algorithms are executed can lead to significant reductions in resource usage at scale. For example, optimizing how data is processed or reducing redundant computations can decrease the heat generated by servers, thereby reducing the need for intensive cooling. While these changes may seem minor individually, their cumulative effect across millions of servers can be substantial. However, there is an inherent tension within the AI industry. On one hand, companies are competing to build larger and more powerful models, driven by market demand and technological ambition. On the other hand, there is increasing pressure to reduce environmental impact. These two forces are not always aligned. Larger models typically require more resources, which can lead to higher water consumption unless offset by significant efficiency gains. This tension raises a deeper philosophical question. What does progress mean in the age of artificial intelligence? Is it defined solely by performance and capability? Or should sustainability be an equally important metric? As AI becomes more deeply embedded in industries ranging from healthcare to finance to entertainment, the answer to this question will shape the future of technology. Public awareness also plays a crucial role. As more people learn about the hidden costs of digital services, consumer behavior may begin to shift. Just as awareness of carbon footprints has influenced choices in transportation and energy, understanding the water footprint of AI could lead to more conscious usage patterns. Businesses, particularly those built around AI-driven services, may need to consider how sustainability impacts their brand and customer trust. Ultimately, the growing attention to AI's water consumption is a sign of a broader shift. Technology is no longer seen as separate from the physical world. It is recognized as deeply interconnected with it. The servers powering artificial intelligence are part of the same ecosystem that provides drinking water, supports agriculture, and sustains life. As this realization takes hold, the conversation is evolving from curiosity to responsibility. The next stage of this exploration will look ahead, examining future scenarios, potential risks, and whether artificial intelligence can become not just more powerful, but truly sustainable. Looking ahead, the future of artificial intelligence and its relationship with water will likely be shaped by a combination of technological breakthroughs, regulatory frameworks, and global environmental pressures. The trajectory is not fixed. There are multiple possible paths, each with its own implications. At one extreme, AI could continue to expand rapidly without sufficient regard for resource consumption. intensifying water stress in already vulnerable regions. At the other, innovation and policy could align to create a more sustainable model where the growth of AI is decoupled from the depletion of natural resources. One of the most critical variables in this equation is scale. Artificial intelligence is no longer confined to research labs or niche applications. It is becoming embedded in everyday tools, from search engines to content creation platforms, customer service systems, and beyond. As adoption accelerates, the demand for computational infrastructure grows in parallel. This means more data centers, more servers, and, unless significant changes are made, more water consumption. Climate change adds another layer of complexity. Rising global temperatures increase the need for cooling across all forms of infrastructure, including data centers. In warmer climates, this can significantly amplify water usage, especially during peak heat periods. Regions that are already experiencing water scarcity may face compounded challenges as both natural and technological demands converge. The intersection of AI growth and climate stress could therefore become a defining issue of the coming decades. However, there is also reason for cautious optimism. Advances in hardware design are beginning to improve energy efficiency, which in turn can reduce heat output and cooling requirements. Next-generation chips are being engineered to perform more computations with less power, a shift that could have a cascading effect on resource consumption. At the same time, alternative cooling technologies are gaining traction. Liquid immersion cooling, for example, submerges servers in non-conductive fluids that absorb heat more efficiently than air or traditional water-based systems. If widely adopted, such technologies could significantly reduce reliance on water. Another promising direction is the geographic redistribution of data infrastructure. Companies are increasingly exploring locations with naturally favorable conditions, colder climates, access to renewable energy, and abundant non-potable water sources. In some cases, this has led to the construction of data centers in regions like Scandinavia, where low temperatures reduce the need for artificial cooling. This strategic placement can dramatically lower both energy and water usage, though it also raises questions about global equity and the concentration of technological infrastructure. The concept of water-neutral or even water-positive data centers is also emerging. Some companies aim not only to reduce their water consumption, but to replenish more water than they use through investments in conservation projects, watershed restoration, and improved water management systems. Microsoft, for instance, has publicly committed to becoming water positive in the coming years. While such initiatives are still in their early stages, they represent a shift in how companies think about their environmental responsibilities. Yet even with these advancements, the fundamental challenge remains. Demand is growing at an extraordinary pace. Artificial intelligence is driving a new wave of digital transformation, and with it comes an ever-increasing need for computational power. Efficiency improvements can help, but they must outpace the growth in demand to achieve a net reduction in resource consumption. This is a difficult balance to maintain, especially in a competitive industry where performance often takes precedence. There is also a broader societal dimension to consider. As AI becomes more integrated into economic systems, its environmental impact may become a factor in policy decisions, investment strategies, and even consumer behavior. Governments may introduce stricter regulations, investors may prioritize sustainable technologies, and users may begin to favor platforms that demonstrate environmental responsibility. These shifts could create powerful incentives for companies to innovate in ways that align profitability with sustainability. In the end, the question is not simply whether artificial intelligence is using too much water, it is whether we, as a global society, can guide the development of this technology in a way that respects the limits of our planet. AI has the potential to solve some of humanity's most pressing challenges, but only if its own footprint is carefully managed. The story of AI and water is still being written. It is a story of hidden costs and visible benefits, of rapid innovation and emerging awareness. And as we stand at this intersection of technology and nature, one thing becomes clear. The choices made today will determine whether artificial intelligence becomes a burden on our resources or a tool for preserving them. In the end, the relationship between artificial intelligence and water is not a simple narrative of harm or benefit. It is a reflection of how humanity chooses to build and scale its technologies. AI, like any powerful tool, amplifies both our capabilities and our responsibilities. It has the potential to revolutionize industries, accelerate scientific discovery, and unlock entirely new forms of creativity and productivity. But at the same time, it brings with it hidden costs that cannot be ignored. Water, unlike many other resources, is irreplaceable. It sustains ecosystems, supports agriculture, and is essential for human survival. When a technology begins to draw significantly on such a resource, even indirectly, it forces us to rethink the true cost of innovation. The invisible nature of AI's water consumption makes this challenge even more complex. Users interact with AI systems through screens, often unaware that their digital actions are connected to physical processes happening far away in massive data centers. And yet, this awareness is growing. As more research emerges and more attention is drawn to the environmental footprint of digital infrastructure, the conversation is beginning to shift. Companies are no longer judged solely by the performance of their technologies, but also by how responsibly they operate. Sustainability is becoming part of the equation, not as an afterthought, but as a core expectation. The future will likely depend on balance, a balance between innovation and conservation, between performance and efficiency, between global access and local impact. Artificial intelligence does not have to be an environmental burden. With the right investments, policies, and technological advancements, it can evolve into a system that is both powerful and sustainable. But this outcome is not guaranteed. It requires conscious decisions from developers, companies, governments, and even users. It requires transparency, accountability, and a willingness to prioritize long-term sustainability over short-term gains. Most importantly, it requires a shift in perspective, an understanding that the digital world is deeply connected to the natural one. So is artificial intelligence consuming our water? The answer is not a simple yes or no. It is a growing force, one that is already impacting global water resources, but also one that holds the potential to become far more efficient and responsible. The direction it takes will depend on the choices we make from this point forward. And perhaps that is the most important takeaway of all. Technology does not exist in isolation. It is shaped by human intention, guided by human values, and ultimately accountable to the world we all share.